Welcome to TARTLEcast with your hosts Alexander McKegg and Jason Rigby, where humanity steps into the future and source data defines the path.
You don't have your alien shirt on today.
No, I know. I've listened to that lady talk so many times. I don't even listen to her anymore. I just know it's go time.
It's go time.
Yeah, I know it's on, and then when it stops,
Let's dig.
Yeah, let's dig. Okay, MacArthur. So we always everybody likes to look up at the stars.
Mm-hmm.
If you don't, well, you're interesting. You probably don't like Disney World either. So
Yeah.
but or dogs.
Yeah.
Nice fluffy blankets. Cozy. You probably don't like being cozy.
How do we go from wolves to domesticated dogs? I know they're working on that. I think I have an article for that we're going to talk about to one of our future episodes.
I want to be
it had to be, when you think about it, it had to be, because I read the article, so I think I put it in one of our, because we use Asana.
Yeah.
Shout out to Asana.
Yeah,
and
thank you.
They were talking about, they had just found bones of dogs that were buried next to tribesmen in like Siberia area. Mm. And they were decorated. The dogs were decorated, and it was like very intentional.
Well, they probably in some way, worship that dog.
Yeah. Or they went along in battle with them maybe,
yeah.
Or, they were like man's best friend, but
I'd love to see the first guy to be like, I'm going to domesticate this thing.
Yeah. But then it's like, I just had pictured these guys sitting around a fire. Mm-hmm. And then the wolves are out there howling. But then there's one wolf that's kind of curious. And then a guy gives him a little bit of food. And he comes a little bit closer. And he comes a little bit closer.
Should I trust this guy? Latches onto his forearm. He's like, yeah.
And then,
well, wait a minute. Can we still save the relationship?
Yeah. It's like a furrow. Because animals, we don't recognize this, but animals are wild.
They are wild.
I mean, they're just being an animal.
And we always go up with assuming that they think and act like a human being.
But is it everyone that goes to the fire a little bit quicker, and then it's just thousands of years, and it's just domesticated? Next thing you know, you go from a wolf to this super lovable golden retriever.
Yeah, or a doge.
Yeah.
And then it turns into a cryptocurrency.
Yes. Which I bought more. It went down, and I bought more.
Good for you.
I don't know. It's just a fun thing. Whatever.
I don't care.
It's gone up. I made $247 so far. I know. Isn't that exciting?
That's great. Good for you.
Cryptocurrency.
Dude.
Off a Dogecoin.
It's like 2 weeks worth of groceries for you.
Yeah.
Good for you.
Or a week's worth.
Gosh, your consumption rate's so high. So is mine. We just eat a lot.
I know, yeah. Especially when, you do a lot of climbing.
Yeah.
And then when you go to the gym and you work out really hard.
Yep.
You just need more fuel.
The
intermittent fasting doesn't work for me. I tried that so many times.
Dude, fuel is key for growth. Not only for us.
Yes.
But also for stars that are forming in the night sky, in nearby galaxies.
How did you go from climbing to nearby, not far away galaxies, nearby?
You want to know why? Because everything's interconnected. You just got to look at it.
Yeah.
So
this article, How Stars Form in Nearby Galaxies, you're like, why are we talking about stars? Why are we talking about galaxies? Well, listen to this.
Stars are cool, and so are galaxies.
Robert Feldman sheds new light on this topic with the help of a data-driven observational measurements.
No pun intended, because it's stars and there's light.
Yes.
Yeah. Data-driven methods. So what we want to do is we want to take tons of photographs of stars, which have a range of 1 to 8 or 9 billion years for their development. For one star.
Yeah, and it's born in dense clouds of molecular hydrogen gas that permeates interstellar space. Mm-hmm. And then physics of star formation is complex. Recent years, they've seen this substantial progress towards understanding how stars form in a galactic environment. But here's the question they wanted to propose to data.
I like this.
What ultimately determines the level of star formation in galaxies?
So what they're finding out, like your car, if I want to ultimately know how long I can drive the car, is going to be dependent on how much fuel I have. So having these interstellar molecular gases, if there's enough of them, fantastic. But then how efficient is my engine? Am I using a lot of it very quickly to develop these stars, or do I use very little over longer periods of time to develop that star?
Right.
And so what they're doing is they're taking tons of these, different spectrum photographs of these nearby stars that are growing, and they're saying, let's look at the changes over time in the amount of molecular gases that we have here and the size of the star as it begins to grow, or the number of stars that are growing. And then we can analyze the rates in a Bayesian statistical model. So what that's saying is, okay, here from observation is our very first look. We've taken these pictures. Here's the first model. Let's look at the rate. Okay, now that we've observed it, there's actually a variance in that rate. We need to go back and retune the model's original hypothesis. So every time they take a new photo, it's coming back in and retuning that stochastic model so that they can find a normalized curve for the amount of stars, how big they are, the amount of gas, and how fast that gas is depleted. So that's the general idea in the big data sense is, okay, if we're observing, taking tons of information, and watching those small changes happen, something that would be very difficult to do for the human eye, we can facilitate big data in these learning algorithms to normalize our curves and understand, okay, we know for sure that if we see this volume of molecular gases in space, we're going to have a star formed in 1 billion years or 9 billion years. We're going to have one of them or 10 of them.
Yeah, and they're looking at the physics of the gas to star conversion. So they look at gas inflows, outflows, and gas consumptions. Mm-hmm. And so that was their, and then gas depletion time scale and measuring gas masses reliability. So now we have all these detection limits. So now we can look at this as a data packet.
Yeah, isn't that just amazing? You have a satellite taking images, and it's measuring gas content from something that is freaking light years away. That is astonishing.
Yes.
If you really wrap your head around it, it's truly incredible to look at something like that. And what they're doing is they're creating this data-rich data packet. And how cool if we can get, remember we talked about the Rubin Observatory?
Right.
What if we could get all the observatories around the world to start packing in these data packets? Now we've had one telescope doing all this analysis, and we compare it with another one, and we can have a real big supercomputer analyze the whole thing.
Yes.
Because now we've collected insights from all these observatories. Right over here in New Mexico, as you're on your way to Socorro or past Socorro, where you go to the Very Large Array, if you look left on the mountainside in Magdalena, there's this beautiful brand new observatory that sits up there. But you'd never know. It's just like a blip on top of a mountain, but it's collecting so much information. So how do we share something that's so decentralized and disparate, collecting all its info with all these other pieces around here? Collective knowledge is a lot of good stuff. I bet you they could solve and normalize that, that gas usage model for star formation a lot quicker.
Yeah, and this is what they talk about, and this was a SciTechDaily.com article. It will be paramount to continue the development of statistical and data science methods to accurately extract the physical content from these new observations and to fully uncover the mysteries of star formation in galaxies.
Yeah, that's so cool. That gets me so fired up. It's so interesting to think that even our sun, which is massive, is puny compared to so many other things out there. For instance, if you compare it to just Betelgeuse, which sits in Orion's belt, it's one of the biggest observational stars around us, this blue supergiant. But all that came together was gas forming. And because it sits in an environment of no gravity, it creates this massive, perfect sphere, and everything's just kind of fallen into itself under its own gravity. It's just amazing. It's this cycle of implosion and regeneration. If I want to give someone some secrets to some interesting physics, implosion regeneration, right? Look at the design of an apple, toroid structures, stuff like that. But, it's amazing that our world and who we are, our physical body, this material, has come together because of stars and molecular gases and things just binding and swirling. And it's incredible that we now have the power to observe it. And if we want to accelerate that observation, we collectively need to take all that telescopic data from all the observatories and bring them all together at once. Big data is going to do a lot of good. And it's awesome that, we're trying to understand what's going on in our galaxies, but it's equally just as important to understand what's going on with us internally as a human being.
Yes, and if you're observatory and you want to work with TARTLE, you can go to tartle.co and sign up.
And if you're low on funds for your observatory, we'll open up a new annuity stream.
Yes.
Start selling the data that you have coming out of that observatory. Hello.
Yeah, we'd love to be able to have a conversation with you. You can go to tartle.co.
Thanks.
Thank you for listening to TartleCast with your hosts Alexander McKegg and Jason Rigby, where humanity steps into the future and source data defines the path. What's your data worth?